Hi, it's time for another math easy solution. To discuss some mathematics for a change. If you've seen my earlier videos, I've been taking a bit of a hiatus to go over suppressed science, like this part, and you can go check those earlier videos that I made. Anyways, in this video I'm going to go over parametric equations and polar coordinates and go over the true-false quiz and its solutions. This is basically a end of chapter quiz in my calculus book, and I thought it was a good way for just to recap on this since I haven't done a math video in a while. And yeah, it's good for mainly for myself, just to get caught up in all the mathematics. And also I highly recommend just downloading this video browser extension to increase video playback speed. Absolutely amazing. Anyways, let's just jump right in and look over parametric equations and polar coordinates and go over the true-false quiz and its solutions. So, as I stated earlier, at the end of each chapter of my calculus textbook, there is a true-false quiz which provides a good recap to test your understanding of the topics covered in that chapter. And since I've been stuck in the wonderful world of free energy, anti-gravity, and gyroscopes for these past few months, going over this quiz will be a good recap to get back into the groove of my mathematics video tutorials and a break from my hashtag suppressed science videos, or I like to call them, real science. Anyways, let's just jump right in. So here is the true-false quiz, and basically we're asked to determine whether the statement is true or false. If it is true, explain why. If it is false, explain why, or give an example that disproves the statement. And there are 10 questions here, and if you could pause the video and just go over them yourself before the solutions if you want to test yourself. But anyways, we're gonna just jump right in and go over number one, the solution to it, and go over all 10 questions in this one video. Alright, so question 1, or statement 1, states if the parametric curve x equals f of t and y equals g of t satisfies this function here, the derivative g of t equals to 0. Then it has a horizontal tangent when t equals to 0. Now before actually I cover this statement, I just want to go quickly recap on parametric curves. So recall that a typical graph of a parametric curve is shown below, and it looks something like this. This is the x, this is the y. So we could have something that goes over here, and then it can curve up like this because it doesn't need to be a one-to-one function, because both the x and y are functions of a third parameter. So you could have it go through, basically one x point can have two y values and go through like that. So yeah, it doesn't need to be a one-to-one function. So at this point, let's say over here, just to recap on how it's written. So this point here, we could call this the initial x and y value, or initial point. So I'll call this x0, y0. So this would equal to the same thing as writing, well, f, because this is f of t, the other one is g of t. So we can write this as f of, and then we just have our initial starting parameter t0 or t0, and then g of t 0, like that. And then at this endpoint here, we could call this just the final point of the parametric curve. This is x f, so final, y f, and this equals to as well f of tf. So you just plug in that parameter inside the function f, and then g for the y coordinate, tf, like that. Alright, now that we have the endpoints, and just a generic point would just be x, y, like that, equals to, right here, f of t and g of t, like that. Alright, so now that I've quickly recapped on parametric curves, let's look at this statement again. So if this parametric curve x equals f of t and y equals g of t satisfies g prime of t equals 0, then has a horizontal tangent when t equals to 1. So let's look at that part. So if we're dealing at t equals 1, so we'll just write if g prime of t equals to 0, this is going to be, well, we're going to be dealing with at t equals to 1 here. So this is has a horizontal tangent at t equals to 1. Then what we end up having is, if you recall that the derivative, so then dy over dx in parametric equations, as I showed in my earlier video, it's going to be the derivative of g prime divided by f prime of t. So this is going to be equal to g of t, like that, prime, over this is going to be f prime of t, like this. And where this bottom one right here, is not equal to 0. So always remember that this can't equal to 0, otherwise it's going to be undefined. So in this case, if we plug that in, we're going to get a 0 over f of t, like that. So now right here, what we end up having is, well, this equals to 0 if f prime of t is not equal to 0, like this. Yeah, so it's if this is not equal to 0, and as you can see right here, if it is equal to 0, so we can write over here, if f prime of t equals to 0, then what we end up having is a dy over dx equals to, well, 0 over 0. That's what we end up having, which is undefined. Let's put an arrow right here. This is undefined, so you can't have a 0 over 0. And also recall that this derivative right here, if it's equal to 0, I'll just put a bubble right here, show you what it means. So if the derivative is equal to 0, it just means it's going to be a horizontal tangent. So it's going to look something like this, where we have a curve going up or down, this part right here, and this one right here, this is dy over dx equals to 0, or it's a flat curve right like that. I mean, it's a flat horizontal tangent, so just put like that. So it would be a tangent if it's not equal to 0, so then the statement is going to be false. And here I've written that down. So from the dy dx formulation above, it is clear that if g prime when t equals to 1 is equal to 0, then the parametric curve has a horizontal tangent if dx is dx which equals to f prime of t. Actually, this is a mistake. This isn't actually equal to that. It just ends up being like this, so they would have some terms cancel out, as I showed in my earlier video on parametric curves, so make sure to watch that. So this is only if f prime of t is not equal to 0, in which case it would not be defined, thus statement 1 is false right here. So it's only if this scenario. For example, consider the parametric curve over here, just to get an example of why it would be false. So if if x equals f of t, and let's say it equals to t minus 1 to the power of 3, and then we have y equals to g of t. Let's say this equals to instead just t minus 1 to the power of 2 instead of the power of 3. So now if we were to take the derivative, derivative of this one, and just to see what we have, so what we have is g prime of t, this equals to 2t minus 1, just put the 2 down and minus a power, just using exponent law, and now what we have is at t equals to 1 here, when we plug that in, we get, well, a 2 times 1 minus 1. In other words, we get 0. So this is our g prime of t equals to 0. And now for this one here, so if we take this one, we take the derivative f prime of t, this equals to, bring this 3 down, we have t minus 1, and then we have a 2 there, minus a power there. And now if we plug in at t equals to 1 here, we get a 3, and then this is going to be 1 minus 1, again, squared. This equals to 0 as well. So thus what we have is, by the derivative dy over dx, recall that this equals to g prime of t over f prime of t. So now what we end up having is a, well, 0 over 0. Because this is 0 over 0, and this is, well, not defined. Like this, not defined. Yeah, so we can't just we can't just assume it's going to be 0. It's not defined, and here I'll show you what it ends up being. So note here, just for completeness, what we have is if we were to take the limit. So let's see what the derivative is when we approach it from just take a limit instead of actually equaling to 1. So limit as t approaches 1 of dy over dx. This just equals to limit as t approaches 1 of g prime of t over f prime of t. Now this equals to limit, just keep plugging everything in, so g prime of t, scroll up, that is right over here, 2t minus 1. So we have 2t minus 1 divided by f prime of t, which equals to 3t minus 1 squared. So now what we end up having here is this cancels with this. So what we end up having is this equals to limit as t approaches 1 of 2 over 3t minus 1 squared. Actually, no, not the squares. Squares cancel. So we have something like this now, and notice now when we plug in 1, this bottom part is going to be equal to 0. So this right here is going to be equal to 1 minus 1, which equals to 0. So this whole thing's going to be 0. So what we end up having is a 2 divided by 0. In other words, this is approaching, well, infinity. So we could just write this as equals to infinity. And this is right here a vertical tangent. And now we don't necessarily know if it's going to be positive or negative infinity, and as I'll show. So vertical tangent. But also note again, so as you can see, it's a vertical tangent, so it's not a horizontal tangent. So yeah, the statement is false just by using an example. And now I'll just write another note number 2. Basically, we have to consider approaching one from the left or the right side, because as you can see here, we're going to have either positive or negative infinity. So note limit as t approaches 1 from the right side, so plus side of it, we have 2 over 3 t minus 1, and if it's from the right side, we're going to have, for example, 1.1 minus 1, so as it gets closer to 1, where it's always going to be greater than 0. So this is going to be greater than 0, so we're going to have a 0 over, it's going to be still greater than 0, but it's approaching 0, but it's going to be positive, so what we end up having is well, plus infinity. So it's going to be a positive vertical tangent there. But then if we approach it from the left side, t approaches 1 from the left side, for example, 0.999, then we're going to have 2 over 3 t minus 1. This is going to be less than 1 always, minus 1, so it's always going to be less than 0, and it's approaching 0 there. So in other words, it's always going to be negative. So 2 divided by negative, like close to 0, is going to be, well, negative infinity, like that. Yeah, and here I quickly just move things around and make it a bit neater like that. So that's pretty interesting stuff there. So now if we were to graph this out, so here is using the Desmos graphing calculator. The curve is going to look something like this. There's the t minus 1 cubed and t minus 1 squared, like that, goes like this. And then I copy that again, put there, just use A so you can maneuver the A around. That's this dot right there. So if it's minus 1, it's going to be on the left side. As you move it, as you move it closer to positive 1, it's going to go downwards here. Then you're going to have a negative infinity. But then if you're approaching from this side, yeah, it's going to be positive infinity, like that. So it's going to be down, up, it's positive infinity. And see that sharp point over there. So a very sharp point. So you could even, let's just click this out. And yeah, here's the Desmos calculator. You could see this right here. As you're moving this, move this a bit slower. Go back to here and press play. So it's going there, make it even as slow as you can. And then it's going to become, yeah, very, very small like that. Yeah, actually, I go back here. So at a equals to 1, we have that as at the origin 0, 0, everything's 0. Then as you move this slightly off, yeah, you can see this extremely sharp point. Let's move this around. So yeah, it goes like this, and then it just jumps right from there. Then it jumps upwards perfectly. There, let's just zoom in more and more. So yes, an absolutely, yeah, perfect curve like that. Anyways, see how this looks like further out. Alright, so anyways, it's pretty cool. I just have it from t is negative 10 to 10. So let's go back into this. So yes, note the sharp point at the origin where the vertical tangent occurs. Also note if the statement stated instead that f prime of t is not equal to 0 when g prime of t is equal to 0, then it would be considered true. So if we had a condition where it's not equal to 0, like that, because that's just the only exception. Alright, so yeah, that was quite a long question 1 or statement 1, but I just wanted to cover that in detail just to mainly to recap myself on parametric curves. And now let's look at statement 2. It states if x equals f of t and y equals g of t, if they are twice differentiable, then d squared y over dx squared equals to this right here, d squared y over dt squared divided by d squared x divided by dt squared. In other words, what it's saying is that if these are, you can take the derivative twice, then the second derivative of y in terms of x is equal to the second derivative of y in terms of t divided by the second derivative of x in terms of t. So this is, well, this is just clearly, yeah, this is clearly false, because I actually covered this in my earlier video, but we could see this because if we recall that the derivative dy over dx in terms of parametric equations, it's going to equal to dy over dt divided by dx over dt. So that's the first derivative, and this is again where dx over dt is not equal to 0. And recall in my earlier video when I covered this, the second derivative, well, the way it works is if we just take the derivative dy over dx, yeah, so we're taking the derivative of the derivative. So in other words, we're going to do d over dx of dy over dx, like that. So now notice the similarities between these two. This one is just replacing this y with dy over dx. So in other words, all we're going to do is replace the equation with y. Replace y with dy over dx, like that. So in other words, this becomes d over, and then this is a new y, dy over dx. So this is going to be d over dt of dy over dx, and then divided by dx over dt, like that. And this is our second derivative. So that's the second derivative, like that, d squared y dx squared. This is just in Lagrange, this is a Leibniz notation. I'll explain that in a bit. Basically, this is the derivative, and not just blindly putting a 2 randomly like this. So it's not this d squared y dx squared equals to, so it's not equal to the second derivative of y in terms of t divided by second derivative of x in terms of t, like that. So this is false. So yes, the statement is false, because the statement is saying that this was true. So then this second derivative is that, so that is false. And also I want to make another note here. Just make a note that this notation right here is dy over dx equals dy over dt divided by dx over dt, as opposed to the one before I was writing it as this right here, dy over dx equals g prime of t and divided by f prime of t. It's the basically the same thing that I'm going at. And just to recap, let's write recall that dy over dx, this just equals to f prime of x, like this. So in other words, this notation right here is the Leibniz, or the Leibniz notation. Let's see if I write it right. So this is the Leibniz notation, and this one right here is the Lagrange notation. And here I just wrote notation there. So this is the Lagrange notation, and that's Leibniz. So if we use the prime or the dy over dx, same thing. I'll just put this in a box like that. And now let's look at question 3, or statement 3. Then states the length of the curve x equals f of t and y equals g of t, where t is between a and b, and it's another parametric equation, is this one right here, integral of a to b of square root the square of f prime of t plus the square of g prime of t dt. So now recall that, well, this is in fact the length of a curve from t equals a to t equals b, but with parametric curves the same path can be traced multiple times. Thus the figure obtained from the above equation does not necessarily equal the length of the curve, but the path a particle takes on that curve. Thus the statement is false, as I will explain in a bit, or illustrate it in a bit. Because if you recall parametric curves, you can rotate the same thing over and over again, whereas if it's just a regular xy Cartesian coordinates, it's going to be something like from here to here is the same length, but then with parametric you can loop around many times. So for example, let's just consider an example right here, x equals to, or this following example, x equals f of t, which equals to cosine of t, and also y, this parametric equation, equals g of t, which equals to sine of t. And let's say this is 4, t is less than or equal to 4 pi, and this is greater than or equal to 0, like that. So that's where we're going to be setting this the interval for this parametric equation. So if we recall how this looks like, and let's just draw this in Cartesian, or just in the graph right here, x and y, so the Cartesian or parametric equations form. So what we have now is, if we have this point right here, if this is our x and y, this equals to, well, cosine of t over sine of t, like that. So in other words, if we were to see this vertical side of this is the y coordinate, that's sine of t. And now this horizontal component is, well, cosine of t. Well, also now if we recall that, well, this is cosine sine of t, that's where we begin, that's just the origin. What we have is, well, recall that sine of t, or I'll just write, actually I'll just write it any way you want. So sine of t plus cosine squared of t, I mean, yes, sine squared of t plus cosine squared of t. Recall that this equals to 1. This is the Pythagorean trigonomic identity. So in other words, yeah, this is also, yeah, the Pythagorean one, because it forms a triangle. So it means that the distance from here to here is always going to be equal to 1. So in other words, whatever x and y is, you can the value is always going to be constant, it's always going to equal to 1 from the origin. In other words, we just get a circle. So we just get a circle like that. Just draw this further out a bit better. So we get a circle. Yeah, so we have a circle here, and also note that, well, at t equals to 0, what we end up having is we have, well, cosine 0. Let's put it actually here. I'll write here let's put this like this, at t equals 0, what we end up having is, well, cosine of 0 and sine of 0. Recall that cosine 0 is just equal to 1, and then sine of 0 is equal to 0. So in other words, we get this point right here. So that's when at t is equal to 0 right here. So we have 1, 0, and t is equal to 0. So this just represents, well, the angle t. And then as you go further and further around it, so then if we wrap this around fully, we get a full circle. This is at t equals to 2 pi. But if we were to go even further, extend this out even further, let's keep extending it like this. Now we have this one here is t equals to 2 pi. Now we have 2 equals to 4 pi, like that, pi radians. And this 4 pi right here, this equals to, well, 4 pi equals to 2 loops. 2 pi is equal to 1 full loop. So in other words, we get the length twice. And I'll just write this down right here. This is just a circle. And in this case, this circle, the length is just going to be the circumference, just around it, and circumference of the circle. And if we recall that the circumference of a circle is just going to be equal to pi times the diameter, which equals to, well, 2 pi r, like that. Diameter is just 2 times the radius, and r is, in this case, 1 is equal to r. So this equals to 2 pi times 1, which just equals to 2 pi. So the length of the circle, or this curve, or the circumference of the circle is 2 pi. Yeah, but the issue we have here is if we plugged in this above equation, this right here, which is the arc length, or the length of the curve from A to B. So if we solve that one, so what we go here, so from the integral from 0 to 4 pi now, instead of, yeah, that's our A to B actually. So instead of 0 to 2 pi, we go to 0 to 4 pi, and then what we end up having is, this is of square root the f prime of t squared plus g prime of t squared dt. And now if we were to evaluate this, well, if we look at f of t is just cosine, the other one's sine. So we're going to take the derivative of that. This equals to integral from 0 to 4 pi of the derivative. I'll just write this d over dt of cosine t, and then squared this one, and then plus this part right here, d over dt of sine. So the derivative of that squared dt, like this. And now if we recall that the derivative of cosine of t, that's just going to be, well, negative sine of t, so square root negative sine of t squared, plus here derivative of sine of t, that is just, well, recall this as cosine of t. So the sine is going to be negative, derivative of cosine is negative sine, derivative of sine is just positive cosine, like this. And then we're going to put a squared like that, dt. So then finally we end up having as integral from 0 to 4 pi of square root. Now this one here is just going to be, well, yes, square root. This is just negative sine t squared is going to be positive sine squared t, or just sine t all squared, plus cosine t squared. And then we have the Pythagorean trig identity again. Recall this just equals to 1. So in other words, we get, well, integral from 0 to 4 pi. Yeah, this just equals to 1. The square root of 1 is just 1, so we have 1 times dt. And then integral of just, well, dt is just going to be now t from 0 to 4 pi. This equals to 4 pi, evaluated in, put in, minus 0 equals to 4 pi. And this is not equal to 2 pi, because remember the length was, 2 pi was a circumference. So we get double the length there. And yeah, here I've written that down. Basically, since t increases from 0 to 4 pi, the circle is traversed twice, and the integral gives twice the length or twice the circumference of the circle. And you could even see this when you graph this with our the amazing Desmos graphing calculator. So let's just go over here and see it. So if you have this curve like this, and here this is the cosine t sine t parametric equation, and you need to put t, it graphs the full thing there. If you write a instead of t, just another variable, you'll get this point particle right here, or this one point there. And as you can see here, let's just start off from 0. Move it to 0. So it starts off at 0. It's right there at 1 and 0. And let's press play. And notice how it goes all the way around. And then yeah, so it loops twice around and goes back. Absolutely amazing. Start again. It goes one full loop and then another one. And that's going to 4 pi. Absolutely amazing stuff. So yes, notice how the particle traces the circle twice. Hashtag amazing. And now let's keep marching along. So we'll look at statement 4. If a point is represented by x, y in Cartesian coordinates where x is not equal to 0 and r theta in polar coordinates, then theta equals to tan or inverse tan of y over x. Well, let's just take a look at that. Let's draw this out in Cartesian, x, y. So let's say we have a point over here. This is going to be our x and y, and let's say that's also our polar axis. So I'll draw this across there. This is going to be our r. This is going to be right here r and theta, where this is the angle theta to this line r, and from the polar axis make it the same as this x-axis, like that. So if we have this, then what we end up having is, well, the vertical component, this is just y, and then the horizontal component, that's just x. So now if we recall from our earlier video, or earlier trigonometric videos, you should know this by now if you followed this along this far, recall the tangent of theta of this angle is defined as, well, y over x, or opposite over adjacent for this case, but it's always going to be y over x. Opposite over adjacent, adjacent, like that. And this equals to, well, opposite is y over x. So then the inverse of this is basically, we would switch these variables around. So theta, theta is going to be equal to inverse of tan. And then tan, inverse of tan of x, y, like this. And this is also where, well, where this x is not equal to 0. So this right here, x is not equal to 0, or else write where. Otherwise, you're going to get a undefined. It's going to go to infinity, like that. So in other words, they already added that exception, so where x is not equal to 0. So then this is, well, true. I think that's our first true statement. Yeah, that's our first true statement so far in this quiz. Very interesting stuff. And now before I get to question 5, I just want to go back and write another note on the Leibniz and Lagrange notation. So if you have something bigger than this, or just go the second power or the second derivative, this would be in Leibniz notation d squared y dx squared, and it's the same thing as writing, well, f double prime of x, like that. And if you're getting really large numbers, you can get, or really large derivatives, you can go like, for example, 4. This is d4 dx4. This part we could just write this as f of 4, like that, with a bracket. So in other words, in general, you just have dn d to the power of n dx n equals 2 f bracket n, like that. And we could box this out, and yeah, just box this out like that. And this is also, yeah, this is Leibniz notation, and this is going to be the Lagrange notation. So yeah, so let's just scroll back here. Alright, so now let's look at statement 5, and this one states the polar curve r equals 1 minus sine 2 theta and r equals sine 2 theta minus 1 have the same curve. Well, first thing we should note from this is that, well, these are very similar. In fact, if we call this r1, so r1 equals to 1 minus sine 2 theta, well, this one is, if we just factor out the negative, it becomes this one. If we just take a negative out, this just becomes positive, this is negative, so we have sine 2 theta minus 1, and that's just this part over there. So this just equals to negative r2. So in other words, these are just negatives of each other. And now that's actually our first clue that they could have the same graph, because if you recall my earlier videos on polar equations are set up like this. What if we have the polar axis there, say we have a point over here, and this is the distance from the pole is r, and then right here is the angle theta. So this is going to be r and theta, like that. Now this is also, yeah, let's just say that we're going to deal with this r as r theta over here. So this is equal to, well, r, replace it, 1 minus sine 2 theta and theta, like that. So that's what that equals there. And now when we deal with negative values of r, because these are negatives of each other, recall that a negative r and theta would just be the same angle here, but then you would go backwards exactly the same distance. So the same distance of absolute value of r all the way to the negative, like here. So I mean all the way to this point right here, and this is going to be negative r and theta, like that. And we've already determined that negative r of this one, well, that's just this function over there. So negative, so you could even move this over there. It's going to be negative r1 equals r2. So in other words, just put a negative there. This just becomes sine 2 theta becomes positive, this becomes negative, minus 1 and theta. But also note that if instead of using this theta, let's say we used an angle all the way across here. So to do that, instead of just using that angle and using negative, what we could do is just, well, add the angle. So this one's going to be, this is a perfectly 180 degrees, or let's write 180 degrees, which equals to pi radians right over here. And by convention for polar curves, we're dealing with radians. So it looks something like that. So in other words, all the way to this point right here, this can also equal to, I'll just write or, yeah, instead of dealing with negative r, we could just use r and theta plus pi. So in other words, this r is going to be, it's a function of theta, but now we're replacing with theta plus pi. So instead of sine 2 theta minus 1, that's negative r, we're going to have the same r. So we have 1 minus sine, and then we have, put a bracket like this, 2 theta, actually put another bracket, theta plus pi, like that, and theta plus pi. So that's what we have right over here. Then if you simplify this further, this just equals to 1 minus sine, and then we have 2 theta plus 2 pi, like that, and theta plus pi, like that. I'll just put this in square brackets, because we have these ones in round ones like that. So now the question is, if this is actually r, well, does this actually equal to 1 minus sine 2 theta, which equals to r? That's the question. That's equals to this r right there. And in fact, it does, as I will show you. Yeah, so recall that the trig function, or the sine curve function looks something like this. Let's write it over here. If this is, I'll write this as 2 theta, and this is sine 2 theta. Recall it looks something like this, goes up and then down and then repeats itself like this. Similar across here. It just repeats itself. Make this a bit lower, like this. Alright, so then at this point here it's 0. At this point right here, this is 2 pi. So recall that the period, and we're just using 2 theta as the x-axis, just to have the same variable there. It could be any variable, but using this one just for just convenience. So now what we have, this period is 2 pi, and then it starts repeating itself right here. So in other words, from here to here is exactly the same thing. So we're just going to be now shifting it all the way by 2 pi. So in other words, sine 2 theta equals to sine 2 theta plus 2 pi. So it's exactly the same thing. Or you could just use the trig identities that I've covered in my earlier video. So that's the same thing as this one right here. So this is actually true. And also if we go backwards over here, instead of having this, we could have a negative r. So we could also have, or negative r and theta plus, this one's theta plus pi. And the negative r is just negative of this one here, because this is exactly the same thing. So put this here, check mark there. So the negative of this one's going to be, well, just going to be sine 2 theta minus 1 and theta plus pi. So it doesn't matter where you go, it's going to be exactly the same curve. So this is the same curve. Yeah, so thus in polar coordinates, the curves r equals 1 minus sine 2 theta and r equals sine 2 theta minus 1, which are just negatives of each other, are the same curves, thus the statement is true. And now if you were to graph this using the Desmos graphing calculator, it looks something like this. For here, I've graphed it in both Cartesian and polar. Here's a Cartesian. So y equals 1 minus sine 2 theta. It looks something like this, goes up and down. But then the green one is y equals sine 2 theta minus 1. So it's exactly the same thing, but negative. So this is positive, and then this one right here is negative all the way there, but it's exactly the same thing. But notice the curves are different. So they're different, but for the polar, we have r equals 1 minus sine 2 theta in red. That's this one around. And then the dots, blue dots, r equals sine 2 theta minus 1. That's just dots around it. So, and it's exactly the same path there. And look at this pretty interesting infinity sign. So note that in Cartesian coordinates, the two curves are not the same. Hashtag very interesting. Also note that in polar coordinates, r represents the distance from the pole, whether the function gives positive or negative values. Or actually, I should have said regardless. Regardless if the function gives positive or negative values, it will just be at different points of the angles. So notice here these are positive or negative, but it's the same distance absolutely, or in terms of absolute values from this one right here. If it's r, if it's negative r, it's going to be the same distance. And if you have the same angles, it's going to follow the exact same path, but in just varying angles to begin with, but it's going to be the same thing. So yes, very, very fascinating stuff indeed. Alright, so now let's look at statement 6, and this one states the equation r equals 2, x squared plus y squared equals 4. Actually, I mean equations, and also the last one is, and x equals 2 sine 3t, y equals 2 cosine 3t, where t is between 0 and 2 pi, all have the same graph. So this is a very interesting statement or a question here. Basically, we're dealing with polar, Cartesian, and parametric equations to see if they all have the same graph. Let's look at the first one here, r equals to 2. This is just a polar curve, and recall that this just means the radius is equal to 2. So if we were to graph this out, x, y, looks something like this. This is the angle theta, and then this is going to be a constant equals to 2. This is always like that. So in other words, all we're going to get is a circle. Whatever the angle is, as you go around, you're just going to get a full circle. So it's just going to be like this, a circle. Alright, so here, we have a circle. Let's write that down, of radius 2. And now let's look at this one right here. Now the Cartesian coordinates one, x squared plus y squared equals 4. So this is just x squared plus y squared equals to 4. And now in this one here, well, recall that this is, well, just an equation of a circle. So let's recall that a circle in Cartesian coordinates is just x squared plus y squared equals to, well, r squared, radius squared. In this case, it's 4, so it's just equal to 2 squared. Yeah, so thus this also represents a circle, and this is with radius equals to 2, and center is at the origin. This is the center of it is at the origin, 0, 0. So it's the same exact one as this right here. And now if we look at the last one right here, x equals 2 sine 3t and y equals 2 cosine 3t, where t is between 0 and 2 pi. Let's look at that. That's in parametric equation. So we have x equals 2 sine 3t and y equals 2 cosine 3t. I believe that was right. Let's see. Yeah, 2 sine 3t, 2 cos 3t, and this is 0. And now we have 0, or t, is between 2 pi and 0. Alright, so now what we have, if we were to graph this out in just Cartesian coordinates, or Cartesian and parametric form. So we have x and y, like this. And now if we have this point right here as our x and y, this equals to, well, just 2 sine 3t and 2 cosine 3t. I'll just write this down, cosine 3t. Alright, so we have it over here, but also I want to note here is at t equals to 0. Let's see where the starting point is. At t equals to 0, we have, basically what we end up having is, well, actually instead of that I'll just write at, let's write this, the coordinates x and y at t equals to 0. This becomes, well, sine 0, 2 sine 0 and 2 cos 0. And recall the sine 0 is 0. This one cosine 0 is 1. So we're going to have 0 and 2 times 1 is 2. So in other words, it's going to be starting off somewhere over here on this side. Yeah, so it's going to actually start off on the y-axis. So what I'll do now is I'm going to draw a line like this. And this is going to be the x coordinate right here. This is 2 sine 3t distance, and this one right here is the vertical component, which is 2 cosine 3t. Now the reason I'm doing it that way is because, well, this is going to be where our t is going to be, and I'll show you it's an angle. In fact, this is a right angle, so make this a bit better, like this. Alright, so we have that. I'm going to box this one out. And now what we're going to do is draw a line across here just to show that this is always going to be constant. I'm just going to call this r. So now what we'll have here is, if we recall the Pythagorean theorem, what we have now is, well, this right here, r squared, is going to equal to the sides squared. So this equals to 2 cosine 3t all squared plus 2 sine 3t all squared, and then if we square all these, this becomes, well, 2 squared is 4 cosine squared 3t plus 4 sine squared 3t. And then we could just factor out the 4. This equals to 4, and then cosine squared 3t plus sine squared 3t. In other words, this is just, well, the Pythagorean theorem. I mean, the Pythagorean trigonomic identity, I mean. So this is equal to 1. This is cosine squared plus sine squared, whatever the variable is, as long as they're the same, equals to 1. So in other words, we end up having is r squared equals to 4. So r squared equals 4. If we square both sides, we get r equals to, well, plus or minus 2. And for our case, to make sense of it, we'll just pick the positive one. Let me know what would happen if you put negative instead. But anyways, this equals to r equals to 2 is the distance. So we'll consider it as positive, equals the distance over there. So in other words, this is going to be constant. This is 2, and that's constant. I'll write that emphasis on it. Constant. So in other words, whatever t is, so initially we have t equals to 0 is going to be on this line. And then as you increase t, what you're actually going to get is a angle like this. This would be t is going to go this way. because these are all going to be positive for the initial values, and it's going to loop around, and this is going to be a circle. Alright, here I just moved everything down a bit just to graph this out, so it looks something like this, but we're not necessarily done yet. Move this out. And the reason we're not done yet is because we're given an interval of 0 to 2 pi. So now let's look at that in a bit more detail. So what we have here is note that the function is going to look something like this. We're going to graph it from 0. I'm going to write this t, this is y, and I'll just write it as y for generic Cartesian function. So if we have the cosine, it's going to look something like this. So this is cosine, and then it repeats right over here at 2 pi. So this is at 2 pi. Or better yet, I'll write this out like this actually. This is going to be at t equals to, move it down, everything move down, but to the right, t equals to 2 pi, then it starts repeating. And likewise here for the sine, actually I'll just write this down first. This is our cosine t, like that. And I just have it separated there. I'll show you why in a bit. So now if we draw the sine, it's going to look something like this. It's going to max out when this is minimum, and then it's going to go to 0 when this is maxed minimum, like that, and maxed out. It's always the opposite of it. And then it goes over here. So this is our sine of t. Alright, so that's what it is for t, but the thing is we're not dealing with cosine t or sine t, we're dealing with cosine 3t and sine 3t. So what we could do is just change the axis. We'll put a 3 there, it's going to be 3, so now this is going to be 3t equals to 2 pi. In other words, if we rearrange this, move it over, we get t equals to 2 over 3 pi, like that. Yeah, so that's what we end up having is a full revolution, or yeah, let's write that here, full revolution every 2 over 3 pi, like that. And then for a total, this is going to be now a total of, it's because t is between 0 and 2 pi, for total of, and this is going to be, well, 3 times it by 2 over 3 2 over 3 pi, and then those cancel. This equals to 2 pi. So in other words, put that in bracket, for total of 3 revolutions. So so it does eventually make this exact same curve. And the reason I did this is to make sure that we have a full revolution, so it does go around it, and in fact it goes around this like once. Yeah, let's draw this like this. It's going to go around it 1, 2, and then 3 times all the way around. So 3 loops. Fascinating stuff. You know, just right here is a circle, but it's 3 loops. And in fact, this is exactly the same graph as all of these. This one right here, it was just 1 loop. Actually, technically more if you use negative, I believe, like that. But regardless, for the polar one, it can go infinite amounts of angles there. It can go loop on for infinity. You can keep going on and on. So I would assume that it is true. It doesn't matter the exact amount of loops. It's all the same graph. It's all, yeah, the same graph like that. And let's just scroll down here. Alright, so thus, basically, type this out. Thus, all the equations are circles of radius r equals 2. Thus, statement is true. And also, MES note, this is assuming that the parametric circle looping around 3 times counts as the same graph. Since, yeah, also the polar equation r equals 2 can technically represent a circle with infinite loops too. So yes, I assume it's all the same. So anyways, if you graph with Desmos graphing calculator, you get something like this. R equals 2 is in red dots. You can see them vaguely all around. And then this is the Cartesian one, x squared plus y squared equals 4. That's in solid block. This is black interval rectangles like that. So you could see those, and then in orange is the parametric 2 sine 3t, 2 cosine 3t, 0 to 2 pi. So it's all the same graph. So notice how all the graphs pile up on top of each other since they represent the same circle. And also interesting here is I added another one here just to change the interval. So this one's from 0 to 2 over 3 pi. So notice it's in orange. For the parametric one, it gets a full circle, but then if we change it up by to 2 over 4 instead of 2 over 3, we get a 3/4 of a circle. In fact, if we just multiply this by 3 over 4, this cancels. This is equals to 2 over 4 pi. Exactly, this one. Like that. So you get 3/4 of a circle. Yeah, fascinating stuff. So note that the parametric equations form a complete circle at a minimum interval of 0. Between t is between 0 and 2 pi over 3. Lowering this interval to 0 and 2 pi over 4, where t is between, obtains just 3/4 of a circle. Hashtag interesting stuff. And now let's go over statement 7 now. So this one states that parametric equations x equals 2 squared, y equals t to the 4 have the same graph as x equals to t squared, y equals t to the power of 6. Well, let's take a look at this. If you look at this first one right here, we have x equals to t squared and y equals to t4. But notice the y one right here. This just equals to, well, t squared squared, and where t squared is just x. So this just equals to x squared. In other words, we have y equals to x squared is the function like that. So now if we look at number 2, this one right here, x equals to t squared. This one's y equals to t to the 6. This just equals to t squared, and now we have power of 3. So in other words, we have t squared is just x. So we have x to 3. So we have y equals to x cubed. So in other words, these are not the same. Yeah, so we can just write not the same. In other words, this statement is false. They are not the same graph. One is a parabola, the other one is a cubic function like that, the other one's going to be like that. So yes, false is the answer. Alright, so now let's look at statement 8, which states the graph of y squared equals 2y plus 3x is a parabola. Well, let's take a look at that. First of all, recall that a shifted horizontal parabola is of the form, and the reason I'm going over this particular parabola is because there's a y squared, there's another y, so in other words, we're going to have an x equals to a y, and then if we complete the square, you're going to have a shifted parabola, just by experience. So recall that a shifted horizontal parabola is of the form x equals to a, and then y minus k squared, and on right plus h, like that. With origin, so with the origin is going to be at, this is going to be at h and k, like that. So this is, yeah, so if we have everything 0, this can be there, and then you're going to have a k value at the leftmost or rightmost part of the curve, depending on a. Anyway, so that's the origin. Recall, you could see my earlier videos on that. So yeah, let's let's simplify first and complete the square. So what I'm going to do right here is we have y squared equals to 2y plus 3x, and what I'm going to do is I'm going to move this over to this side, so we have all the variables on one side. So what we end up having is a y squared minus 2y equals to 3x. And now if you recall completing the square concept, which I covered in my earlier videos, what we have is if we have a y minus h and then all squared, like that. Let's do this here. This equals to, yeah, this just equals to, well, y minus h times y minus h. So this times itself is going to equal to, I'll just complete it out, write this all complete for completeness sake. So y times y is equal to y squared, y times negative h is equal to negative hy, like this, and then the same thing here, negative h times y have the same thing, so it adds up to negative h, then negative h times negative h equals to plus h squared. So that's what the square equals, and notice this y squared minus 2hy is similar to this right here. So this is what we want. I'll just write this as want. So what we have now is, I'll just write in our case, what we have is basically here we could set these equal to each other. So y squared minus 2y equals to this one right here, like that. So then in other words, this h needs to equal to 1. H equals to 1 in this case. So that's if h equals to 1, so we have h equals to 1, we have is thus, oh yes, let's write this all out. Yeah, let's write that a bit neater. So thus we have h equals to 1, and then we have, so we're going to have this whole, complete the square. We have y minus 1 squared equals to y squared minus 2y plus 1 squared is just 1. And now what we'll do is move this over so we could separate this out. So we have a y squared minus 2y equals to y minus 1 squared minus 1. So now that we have this, notice what this part right here is just 3x. So that's just 3x like that. So this goes down here. This equals to 3x. So now what we can do is divide everything by 3. 3, so cancels that out. We end up having is x equals to 1 over 3 y minus 1 squared. And this is exactly our shifted parabola. Minus 1 over 3. This is just a shifted parabola. Yeah, so this is, well, a shifted horizontal parabola opening up to the right, because it's positive. Horizontal right opening. Put is all down. Interesting stuff. Parabola. And actually I'm going to scroll back up here. So instead of saying with origin, I'll just write with center, or whatever you want to call that. So with center, H and K. Right opening parabola with center. This is going to be now, x is going to be, well, 1 over 3. It's negative, so that to get to the 0 mark, and this whole thing needs to be 1 over 3. And actually, whoops, forgot that. I mean, if this is 0, this is going to be at negative 1 over 3. So not 1 over 3, but negative 1 over 3, and then this one here to make this all 0, y equals to 1. Like that. Yeah, so that is what we have there. So thus, statement is, well, true. Well, statement is true. Write this a bit better. Should I just type this out? But anyways, yeah, the statement equals to true. Like that. And yeah, in fact, it is a parabola. So all we're asked is just a parabola. I just went through a bit extra. It's a horizontal right opening parabola with center negative 1 over 3 and 1. And now if we were to graph this with the Desmos calculator, you have y squared equals 2y plus 3x. We get, well, a right opening horizontal parabola with the center, or origin, whatever you want to call this one, at negative right here, 1 over 3, or 0.333, and it keeps going on, and 1. That's exactly what we had. So the statement is true, yeah, as can be seen from this horizontal right opening parabola. Fascinating stuff. And now let's look at statement 9. This one states, a tangent line to a parabola intersects the parabola only once. Alright, so by intersects, what this means actually, so MES know this question actually is meant to say a tangent line, quote, meets a parabola once, not necessarily moving through it, because you may perceive that with the word intersects. But anyways, we can actually see that this is true, see this whole statement visually by considering a parabola. Just go one that opens upwards. This is x, this is y, like this. Let's just say it opens up like this, or actually make it above here. So it opens up like this. Alright, so see it moves up like that. So now we're asked a tangent line to a parabola. If we had a tangent line anywhere here, for example, notice what happens here. This is going to be a tangent line like this. It's going to only touch once. If we had a tangent line over here, it's going to be on the outside. So put this down like that. It's going to be on the outside. If we had one somewhere here, it's going to be vertical or horizontal, and it's never going to touch. So one over here, it's only going to touch once, I mean. So once and then never touches it again. That's how it's going to look visually. Yeah, so here, just type that out. So note that the parabola never gets close to tangent line the further away, or actually worded better, note that the parabola gets further away from the tangent line as you move further from the point of intersections. If you have one here, as you get further and further, it's going to be a bigger and bigger separation, and either way you move it, it's always going to be bigger and bigger. Thus, the statement is true in that tangent line to parabola intersects a parabola only once. And we could also see this numerically, and we could do this by, well, assuming we have a parabola of the form, yeah, let's say we have parabola like this, y equals to cx squared, where c is greater than 0. And let's find a tangent line or line tangent to parabola at this generic point x equals to a. So this one's just going to be positive, so it's going to be an opening up with the origin is the center of that parabola, so y and x is going to look something like this, and this is going to open up like that. So this is our y equals to cx squared. And let's say we have a point right here. This point right here is going to be our x and y, which equals to, in this case, well, this is a. So this is at a, so it's actually going to be, well, a, and the y point is there, so ca squared. And now if we draw a tangent line, let's just draw one like this. It's going to go up like that. And what I'm going to do now is, let's say on this tangent line there is a point here, x and y, and I'm going to draw this point here all the way is going to be x. And I'm just going to say this is our tangent line. Alright, so then this distance right here, this triangle, we're going to get a triangle like this. This is going to be, let's draw that a bit solid like that, and this one's going to be like that. So a triangle like this, where this distance is going to be x minus a, and then the vertical one is going to be y minus this distance right here. This is from here to here, ca squared, so that's of the parabola, ca squared. Yeah, so then this triangle is going to have the same slope as well, just generic m there and 1. So rise over run, and that's going to be the slope of this line, and it's going to be at the same derivative over at this point at a of the parabola. So in other words, so we have a tangent line like this, where this triangle, rise over run, let's write that down, rise over run, or equals to slope, which equals to our m, m over 1 if we do that, or this, in this case, that triangle, I guess, y minus ca squared over x minus a. Now this equals to, well, the derivative of this parabola there equals to the derivative d over dx of this derivative cx squared at, I'll put this like that, at x equals to a. So what we end up having is this is going to be now equals to over here. The derivative of this is going to be, well, c, there's going to be 2 there, 2cx, and then this is at, again, x equals to a. And then now what we have, just plug that in, we get, well, 2ca, like that. In other words, put that together, we have y minus ca squared over x minus a equals to 2ca. It's just another way of finding the tangent line. There's other ways you could do y equals mx plus b and solve for m and b and so on. Let's do it this way. So now we have an equation, and what I'm going to do is I'm going to multiply both sides by x minus a. So we move this over, so we have x minus a there. So then we end up having is y minus ca squared equals to 2ca, and then x minus a, and then this equals to 2cax, and then we have 2ca squared, and then put this down there, y equals ca squared. And now what we'll do is move this over to this side. So now we have negative ca squared, and this negative ca a squared. There's 2 of those, so when we add that up, this is going to be plus. So what we're going to have is, move it here, y equals to 2cax minus, this is going to be 1 now, ca squared. Because we have a minus 2, then we have to add 1 when we're moving it over. So now this is our equation of the tangent line at a generic point, x equals a. And now we can determine the points this tangent line meets the parabola by setting the 2 equations equal to each other and solving for x. In other words, we have, well, parabola is, let's write that p, we have y equals to cx squared, and then we have for the tangent line TL, we have this point is going to be over there, so y equals to 2cax, like this, 2cax minus ca squared. So let's find all the points for x that these are equal to each other, so set them together. So we have cx squared equals to 2cax minus ca squared. And notice there's a c there, we can just cancel all the c's, all the same thing everywhere, so we get an x squared equals to 2ax minus a squared. And now what I'm going to do is I'm going to move these both on this side, and now notice what we have. We have an x squared minus 2ax plus a squared equals to 0. So we move that over, and notice what we have here. We have just a perfect square, actually. Yeah, this is in fact just equal to, well, x times x. This is actually just x minus a squared, because if we have x times x is going to be x squared, x times negative a is going to be negative ax, but then negative a times x is going to be another one, so we have added 2, then a times the negative a is a squared. So yeah, so we just complete the square right there. This equals to 0. And thus this only equals to 0. This is the only time that it equals to 0 is at, well, thus x, the points that they are equal, x equals to a. So then this just goes to 0. X equals to a like that, and then the points are, and this point right here, x and cx squared. Actually move that down here, and x, and then this one's cx squared. The parabola, the point on it is going to be at a, so a ca squared, like that. And yeah, that's the point. And that's exactly this one right here, scrolling up. That's exactly just this point, a ca squared. So that's just 1 point. And yeah, so this shows that each tangent line meets a parabola at exactly 1 point. We just take a generic x equals a point and find a tangent. We're always going to get just 1 point, because x minus a squared is equal to 0 is only true if x equals to a. Thus, the statement is true once again. And now finally let's look at statement 10, and this one involves a hyperbola, and we're asked, a hyperbola never intersects its directrix. So, to make sense of this question, let's go first recall the unified theorem for conic sections, or recall that the theorem determines a hyperbola for the case where the eccentricity e is greater than 1, where e is defined as the distance pf divided by distance pl, where the line L is a directrix, the point F is the focus, so we're given a focus and a directrix, and then where we have the distance pf is the distance p on this curve to the focus, and then pl is the distance from the point to the directrix, so just a perpendicular line to it. So for a hyperbola, we have the eccentricity is greater than 1. So in other words, what we end up having is, since it's pf over pl, so we have e equals to pf over pl. Yeah, wrote that right. So this means that what we end up having is it's greater than 1. So in other words, if we move this around, what we have is pf is greater than pl, this distance. So in other words, this is greater than pl for a hyperbola. Yeah, so the point is closer to the directrix than the focus. Yeah, so I just typed that out as well. So thus the point P is closer to the directrix L than it is to the focus F at all points on the hyperbola. Yeah, so if we had a standard hyperbola like this opening up horizontally, let's say we had something like this, x and y. So let's say we have the point F, or there's a focus there, and this is our hyperbola, extends out this way. So then if we had this, let's say this is our point that we're considering, that's right on the dot or on the x-axis. So then this is our point P. So this distance is PF. Then if we were to have a directrix, it's going to be perpendicular to this. So it's going to look something like this. It's going to look exactly down the middle here. Or actually, I'll just draw that out, solid line, but a bit thinner. So this is the line L right here. So that's the line or the directrix. So write L, and this is the directrix. And then this distance is going to be shorter than this far one. It's going to look somewhere like this, PL, like that. And now if we go further, now we have to graph the other side of this hyperbola. First, note that the opposite side of the hyperbola also won't intersect the directrix. As you can see by the definition, it's not going to intersect this one. Yeah, and this is because if the hyperbola ever does intersect it, then it won't be considered a hyperbola in the first place, as I'll draw one soon. And as also MES note, as will be explained further in this video, note that for a positive directrix, x is greater than 0, then it will be located to the left of the hyperbola center, and I'll explain. It's going to look something like this. So the center of this is going to be here, and it's going to be h and 0, and I'll show that later as well. So then the other side of this is going to be exactly distance across here to here would be c. And then this is going to be exactly the same distance, c. So then this goes outwards this way. Let's draw this a bit more aligned with it, like that. So then it's going to look something like that, and this one's also going to be, it's going to be further away than this one is to that. So very interesting stuff, and I'll explain why. I'll explain why later in this video, but first I want to show that because, right here, if the hyperbola ever does intersect the directrix, then it won't be considered hyperbola in the first place. For example, consider this graph right here. Let's draw it over here. This one is, it's like this. This is the x, this is the y, and let's say there's the focus again, the f, and then it opens up this way, it opens up that way like that. So then the directrix, let's say that the directrix is going to be somewhere close to this one right here. So this is the line L, and this is the directrix. Directrix, like that. Yeah, so then in this case, let's say this point is P. We have P right here. This is just a point on the hyperbola. Then the distance from P to the line here is going to be very small. It's going to look like it's PL absolute value. But then notice that this full length right here, F to P, is all the way across here. That's going to be, well, PF, like that. So in this case, we have, at this case right here, we have E is equal to, remember, PF divided by PL. This is going to be, well, greater than 1. Yeah, so for this case, it's okay, this part right here, but then the issue is it's not always going to hold true. Yeah, so now let's say instead we have a point over here. So we have a point over there. Instead, let's call this one P, and it's still going to be on this line like that. And then if we draw this distance across here to here, this is going to be, actually that's a bit higher up. I'm going to just squeeze this a bit just to visually see it better. So let's say the point is actually over here, and just squeeze this hyperbola just to illustrate the point. So let's say this point is P, like that, write it over here. So that's this point. So now this distance from here to here is going to be, this is PF, like that. And then this distance, as you can see, is clearly longer than the other one. This is going to be PL to the directrix. So in this case, what we have is E is equal to, remember, PF over PL. PF in this case is smaller than this one, so this is going to be less than 1. So in other words, we have varying E. So this proves that this is not, not a hyperbola. So we can't have it intersect at all. The shape won't be a hyperbola. And here I've just typed that out. So thus, since E, or the eccentricity E, would vary from E is greater than 1 and E is less than 1 if the curve intersects the directrix, then the curve is not a hyperbola. Yeah, so thus the statement is true when a hyperbola never intersects its directrix. Yeah, so now going even further, just because it's a very important example or statement to just clarify in more detail, we can also see this is graphically the case by considering the equation, the polar equation of the unified theorem for conic sections. That's this right here, a polar equation of the form r equals ed over r plus or minus e cosine theta, or r equals ed divided by r plus or minus e sine theta, depending on how you define the directrix. Yeah, it represents a conic section with eccentricity e and the focus at the origin. So then the conic is an ellipse if e is less than 1, a parabola if e equals 1, and a hyperbola if e equals greater than 1. I'm just recapping the definition. Or it's actually just a formulation that's from the definition. That's what I derived in my earlier video. So then we have something like this: r equals ed 1 plus e cosine theta if x is positive directrix, like that, on the right side, and there's the focus on the origin. If it's on the left side, it's going to look something like this. If it's on the vertical up, positive is going to go down. If it's on this one, it's going to go up, like that. This is generic, but then for a hyperbola, you can always obviously have the negative sides. It's going to be a bit further out than this one. So anyway, so if you graph one out, here's an example. Let's have r equals 2d divided by 1 plus 2 cosine theta. And here I picked the directrix as negative 0.1. This one is e, so that's e is greater than 1, and that's equal to 2. So if we have that on the negative side, we get, well, this one right here, where the focus is over here at the origin. So origin is always the focus. And then we have, notice this one is closer than the center point. The center one is going to be somewhere h and 0. And h will be negative in this case. So it's going to be somewhere there. And then notice here, if I make it 0.1 as the directrix, it's going to be now f is this one. Focus is changed. And then notice how, again, this is closer than the center. Center here is going to be somewhere in between here. It's going to be h0 again. So yeah, notice how the directrix line never makes contact with the hyperbola. You can see it's never there, and I'll show you how you can move it around. And notice how, yeah, over here now, if you have the directrix equaling to 0, this goes to 0. So then you'll have r is equal to 0. When d equals to x, which is, yeah, 0, so we have x equals 0 as a directrix, the equation becomes r equals 0, which is, yeah, thus a point at the origin, i.e. not a hyperbola, it's either a point or just nothing there. And here what I've also done is I've added a variable. Instead of writing 2, I put a. So in this case, e equals a. Yeah, e is just equal to a variable, so we can use a slider on the Desmos calculator like this. And here if I make it 1.4, leave d as just 2.5, notice how it's, again, it's off center to the left of it. So the center is going to be somewhere over there, h0. And there's the focus as well. This is to the right of that. But then if we have it as to, or I mean, if we just change this to 4.1, leave everything the same, 2.5. And then also I want to make a note here. Note also that varying e written as a in the Desmos calculator, since e is already defined as the famous number 2.71828, etc. Also shows the directrix. Yeah, it shows a finished sentence closer to the focus. It also shows a directrix closer to the focus over here than the center of the hyperbola. So that's a center. This one's closer than that one, obviously. So in other words, the directrix is not over here. It's not there. So keep that in mind. I'll prove that mathematically soon. So also now if you make it a is 4.1, leave d is 2.5, it's still going to be, it's going to shift, everything's going to shift, but this is going to be still off center to the left like that. This is h0 and there again. Fascinating stuff indeed. Yeah, so now I want to make an important note, MES note. In my earlier video on the hyperbola proof for the unified conic sections theorem, I had made the following misleading drawing. This was in the proof. There's a Steemit notes link to it, and I'll put a description for the video as well, saying I made a mistake. So if you notice here, this is the drawing I had there. I put the directrix, I was a bit lazy, put it somewhere around there when I was determining this. But it's actually wrong. You can't have it there. Yeah, so then this one should actually be somewhere in between here, like that. It should be somewhere there. Yeah, so I'll just draw that out. It's going to be somewhere over there. This is wrong. It should move there, L, to the left of the center. Yeah, so basically this is actually misleading. The directrix should be moved to the left of the hyperbola center point and not intersecting the hyperbola. So from my earlier derivation in that video, also recall that when I was deriving it, I ended up getting to this point, negative h equals to d times e squared over 1 minus e squared. Yeah, so from here, what you can notice now is, well, since for a hyperbola we have e is greater than 1, then what we end up having is if we just square both sides, if e squared is greater than 1. And now you just move this over to this side, and then what we end up getting is, put it over here, 0 is greater than 1 minus e squared. That's this part right here. So in other words, this right here is negative, or it's less than 0 according to this. So yeah, so that's going to be negative. So what we end up having is thus negative h equals to, what I'm going to do is I'm going to put a negative here, and then we'll write d e squared. D is, I'm going to just assume that's also greater than 0. So now this one's going to be absolute value 1 minus e squared. So make it positive by adding a negative sign. And this is for also for the case that d is greater than 0. So we have this one on the positive right side over here. So that's on this side like that. And where the focus is the origin. So we have that. Now what we could do is, well, yeah, just add these, just cancel out the negatives. So we have h is equal to d e squared 1 minus e squared, and this is going to be greater than, because this is always positive, e is always positive, and this is going to be greater than, well, 1. Actually, not 1, I mean greater than 0. So yes, the center is going to be obviously positive, and now what we'll note is also, note that e squared over 1 minus e squared, actually not that way, we'll do it right this way better. So e squared is going to be obviously bigger than 1 minus e squared, absolute value. So the absolute value of 1 minus e squared. This is obviously greater than that, because this one here we're subtracting a difference, so we're always going to have this extra 1 being subtracted, or the other way around. 1 minus e squared of a negative, be all absolute value positive. So this is greater than it. So what we could do now is, what I'm going to do is divide both sides by this 1 minus e squared absolute value. Divide by 1 minus, or let's put it just easier to see. Actually, I know that was pretty good like that. So 1 minus e squared, divide both sides. 1 minus e squared. So then what we end up having is this cancels with this, and this just equals to 1. So in other words, we get this part, e squared divided by 1 minus e squared, like this, is greater than 1, because this equals to 1. So that's this whole section over there. So thus, we have h equals to d times it by e squared 1 minus e squared absolute value. That's this part right there. This whole thing equals to, oh, it was greater than 1. So greater than 1, this whole thing. So then this equals to, or it's going to be greater than 1 times by d, greater than d. Yeah, so thus we have h is greater than d, like that. So then if we scroll up to how this is looked like, notice here h is greater than here, which is x equals d. Yeah, so here I'll write x equals to d right there. So h is greater than d when we have d is defined as positive there. So very fascinating stuff. Yeah, so thus the following figure correctly describes where the directrix is located, assuming the focus used in the polar equation is at the origin. So here, this is a recall from my derivation that was going to be, where the polar equation gives a shifted horizontal hyperbola, like this, x minus h squared divided by a squared minus y squared divided by b squared. And then there is a directrix to the left of h and 0 or the center, like that. Absolutely fascinating stuff. So yes, hashtag interesting stuff. And yeah, this was actually a note I gave to myself. So now, yeah, I'll be updating the older video. I'll just put a link to this one saying made a mistake, and directrix should be over there. So anyways, that's all for today. If you follow along this very extensive math lesson right here, very fascinating stuff. Just scroll up. And yeah, I just wanted to take a break from my hashtag suppress science or hashtag real science videos, and also my research that I'm doing behind the scenes, a lot of experiments with especially gyroscopes, basically anything spinning. It's absolutely fascinating stuff, and I think we're going to get through some real breakthroughs. Anyways, I just want to take a break from that and challenge myself mathematically going through this video. Also great recap on parametric equations and polar coordinates. Anyways, that's all for today. Hope you learn. Like always, you can download these exact notes in the link below, as well as viewing these notes on Steemit. Also make sure to check out my math forums on Reddit and vote. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.